Okay, so let's get started. Good morning again. I'm Jens Oberhalter from Clemson University. I'm one of the conveners of this workshop. This is year 3 about coupling of terrestrial weather to space weather. And again, folks, when you don't want to attend this workshop, could you continue your conversation elsewhere? Yes, that would be helpful. Okay, thank you. So this is year 3 of this workshop where we will focus a little bit more about physical processes compared to the first 2 years where we focused on more baseline data and data assimilation approaches. We have 18 talks in this session, 9 this morning, 9 after the break. Every speaker has 14 minutes, including discussion apart from the last speakers in each session who volunteered to live with a shorter time frame. I ask all speakers, limit yourself please to 12 minutes so that we have 2 minutes for discussion, and Björn, who's a co-convener here, will give all speakers after 11 minutes a white sign, okay, and that's the sign for you to come to an end so that you have 1 minute left so that we can have a little bit of a discussion. And so with that, I would like to introduce our first speaker, Sri Lakshmi from Clemson University.
Hi, good morning all. I'm Sri Lakshmi. I'm a grad student from Clemson University and I'm working with Dr. Xian Lu. So today I'm going to talk about my research, which is atmospheric gravity waves and ionosphere-thermosphere coupling, insights from O, GNSS, and high-resolution vacuum X. So a little bit of background here. As we all know, gravity waves are major drivers of coupling, vertical coupling between the lower atmosphere and the upper atmosphere. And these waves, originating from the lower atmospheric tropospheric sources like convection, thunderstorms, propagate upwards, and these waves perturb the neutral winds. And through ion-neutral collisions, these manifest as electron density modulations or traveling ionospheric disturbances in the F region ionosphere at 300 kilometers. So in this field, a lot of studies have been going on, both observational and modeling studies. And one such example study is shown here by Liu et al. 2024. So they have they have combined magic gravity waves with TiGCM nested grid. They nudged with the TiGCM nested grid to show the impact of gravity waves generated as a result of a severe thunderstorm, a tornado event. And the model have reproduced significant electron density perturbations, as you can see here in TiGCM DTEC, and they have induced TEC perturbations up to the amplitude of about 0.1 TEC units. So this is one such example. But most of the studies are largely event-based. The question of how much of the observed ionospheric variability is driven by gravity waves originating in the lower atmosphere is still an open question. So to address this question, as a first step, we did an observational study using atmospheric waves experiment and GNSS. So this was a coordinated study. And as you can see in this movie, the left panel shows the O gravity waves. And in the right panel, we see the GNSS response corresponding to these waves. You can see concentric TIDs here. And we have done this study, a correlation study using O radiance data and GNSS VTEC. So we found significant correlation, especially during geomagnetically quiet periods. We found that about 65% of nighttime events exhibit strong coupling. And also we saw, as you can see in this figure, we saw the coupling strength decreases with increasing geomagnetic activity. And we know the concept that the nighttime TIDs can be generated by some instabilities as well. So to rule out the possibility of those instability in my study, I took the propagation diagram of GNSS TIDs, and from a statistical, so we did this for like full year 2024. We have like 6 months of data with the continental United States overlap with both the data sets, and we saw most of the TIDs propagated either northeastward or northwestward, and only 14% was the southwestward propagating TIDs, which is considered as the instability-driven, Perkins instability-driven TIDs. So this study showed a pretty good correlation between the mesosphere and the ionospheric waves. But since this is a model study, we have only information at 2 different heights, one at 87 kilometers and other at 300 kilometers. So a lot of information between the atmospheric altitudes are missing. So to validate these observations, we, so these are the major challenges using observational studies. So a continuous vertical tracking of gravity waves from source to ionosphere is not possible. And also the ionospheric disturbances can be from direct gravity wave propagation from below, it can be from secondary wave generation in the upper atmosphere, and it can be due to local plasma instabilities as well. So all these different processes generate the same kind of similar ionospheric signatures. So the science question I am trying to answer here is what fraction of ionospheric disturbances are directly driven by gravity waves from below, and how do these coupling pathways varies with season, latitude, and local time? So to answer this question, here we have incorporated a study using the high-resolution vacuum-X. So here I have used a machine learning framework to track gravity wave packets and to see if we are seeing the same gravity wave signatures in the electron density using the same model data. So yeah, as I said, I'm using the high-resolution vacuum-X. So this is a global atmospheric ionospheric simulation extending from the lower atmosphere to 600 kilometers. And it has a pretty good horizontal resolution of about 25 kilometers, and it has 273 vertical levels. And it can resolve gravity waves with horizontal wavelengths greater than 200 kilometers. So to isolate gravity wave scales and MSTID, medium scale ionospheric disturbances, I have used a spectral filtering. So I have used 2D fast Fourier transform and extracted waves with wavelengths ranging from 200 to 1,000 kilometers. As you can see, in the left panel, we can see the rho vertical winds and the rho electron density. And on the right, we can see the filtered fields waves. So this is a machine learning framework for gravity wave detection and vertical tracking. So from the filtered vacuum-X fields, I have generated random patches at different altitudes and different locations. And I have manually labeled these patches as ring or non-wave. So I have different labeling training data sets, which are coherent waves and non-waves. And the non-waves include the EIA, noise, and some plane wave structures. And I have used these labels to train the random forest model. And so I have trained the random forest, and how the wave detection works is given here. So first we go to the variance map of the vacuum-X fields, and we identify potential gravity wave energy candidates, and we look into wave-like structures that we trained before. And we classify inside the variance candidate detection, we classify it as waves or non-waves, and that's how it detects waves. And after detecting waves at every altitude, we looked into the altitude propagation, like at different levels at 55 to 300 kilometers. And these are the results. So this is the vertical wind at 55 kilometers, and you can see some wave packets here, and same wave packets at 90 kilometers, 150, and 300 kilometers. And you can see the same perturbation in the relative electron density as well. So here in my study, I have considered only coherent wave packets. This model right now is detecting some small waves as well, but sometimes it can miss waves or misclassify waves. I'm still trying to improve this model. So to make the analysis robust, I have selected coherent wave-like structures, as you see here. And I have classified these as primary gravity wave-driven disturbances. And so the primary gravity wave disturbances are obviously waves that shows continuous propagation from 55 kilometers to 300 kilometers. And the second category is possible secondary wave generation, where we did not see a wave below, but we saw waves at higher altitudes, possibly above 100 kilometers, and also some auroral-driven waves, as you can see here. And non-gravity waves. Sometimes we see electron density perturbations without seeing gravity waves, vertical wind perturbations below. So those are categorized as non-gravity waves. And I have computed a coupling fraction using this equation. And I have computed this for 4 different months, December, March, July, and October. I have tracked waves and looked into whether it produces a relative electron density perturbations or not. And these are some statistical results. We see that about 54% of waves propagated upward and induced electron density perturbations. And these are the local time dependence and the latitude dependence. And we see comparatively high coupling fraction on mid to high latitudes. And also we can see a nighttime peak here in this plot. So these are some preliminary results from this framework. So these are my conclusions. So within this 200 to 1,000 kilometer horizontal wavelength range examined here, approximately 54% of detected ionospheric disturbances are linked to gravity waves that can be traced continuously from the lower atmosphere to the ionospheric heights. And we see high coupling fractions in July, which reaches approximately 61%. And again, it is strongest at the mid to high latitudes, and which is consistent with our coordinated OGNSS observations. We also saw like a 65% coupling fraction there. So it shows it's pretty much close. Yeah, it's almost done. So and also the primary gravity wave disturbances occur most frequently during post-midnight to morning local times. And my future work is to improve the model accuracy and also to use control vacuum X simulations to identify the factors governing the coupling. Thank you.
Thank you, Sri. We have a couple of minutes for questions.
All right. Can you hear me now?
Oh, yes. I can.
Yeah, I'm very interested with your work. It's very impressive.
Thank you.
So the question is, have you been validated it with observation? Like OWL or other observation?
Yeah, so the first study we did was the observational study, as I have shown
Maybe I missed it because I joined
here.
late.
Oh, sorry. So this was my first study using, this is a coordinated study using atmospheric waves experiment and GNSS VTEC data. So we studied the correlation between the radiance variance and the VTEC variance, and we saw significant correlation between the two.
That was not my question. The gravity wave structure, you actually capture it from your model. This is very impressive, but I'm just wondering if you validate that gravity wave from observation. I mean,
no, I did not
that was
validate
my
it.
question.
Oh, sorry. Okay, yeah.
Yeah, this is very impressive work. I just wonder if you analyze some other variables rather than vertical wind, maybe horizontal wind or temperature perturbations, maybe that can give you a bit more metrics for the analysis.
Yes, I have looked into temperature as well, but we can see the wave-like structures like more clearly in the vertical winds. I feel like vertical wind is a more good proxy for gravity waves. So, yeah. Yeah, thank you.
So our next speaker is Shunrong Sheng, from, as we all know, from MIT Haystack. We'll talk about MSTIDs.
Yes, TIDs and gravity waves and welcome X, very similar to the previous presentation. So this study is motivated by the fact that we have been observed TIDs with ground-based GPS, and I also know that Hani has been running welcome X for an entire year. So that gave us the opportunity to make a comparison between the long-term measurements with GPS and long-term simulation with welcome X. So this is a collaboration. And just to clarify that Hani is not a part of MIT Haystack, and he's still working at INCA. But anyway, so actually a significant part of this work has been published in JGR this year. Just want to clarify the kind of parameters we have been looking at for the comparison purposes. So we're looking at a differential TEC, and here, in order to the statistics study, we're particularly looking at the intensity of the fluctuations. And the intensity is defined as the differential TEC, the absolute value of differential TEC, as an average in a small region, which is 5 degrees by 5 degrees in space and 15 minutes in time. So we calculate this intensity within each of these pixels globally, and then to looking at the global distribution of the this intensity variations. So this is what I call the ATEC, which is the intensity, and then there's PTEC, which is the relative variation, the ATEC divided by the total electron content, and that is very useful when you're looking at solar cycle variation, seasonal variation, day and night variation. So the relative variation is very important as well. So I hope this is, okay, this is a movie. And this is a global map for December 2023. So this is a monthly average. Over here is midnight. So you can see significant difference between the northern hemisphere and the southern hemisphere because of the seasonal differences. In northern winter, the activity is much lower. In the southern summer, so the activity is higher. That's very classical seasonal differences in the MSTID activities. And to the north is a highlighted region. Those are associated with activities in the polar region. And in the equatorial region, those activities are associated with plasma bubble activities. In particular, in December, we know in the American longitudes, these activities, bubble activities, are very active in December. And this is moving, showing the variation in time, local time. Now it's moving to, I cannot stop it. Okay. So, move that again. Okay. Yeah, so this is changing in time so that you can see the difference between northern and summer has been changing during different local times. I will go into a little bit of details later. Here, I just want to show you, give you an overview of the global picture of activities, TID activities. So this one is similar to the previous slide, except here is in July and northern summer. And previous speaker was talking about the different excitation physics involved in gravity wave and Parkinson instability. And here is a particular example. In northern summer, many Japanese studies has indicated that the MSTIDs are potentially associated with Parkinson instability. So if you're looking at the Asian longitudes, you can see here at median altitudes, there's enhanced activity in both north and south. So this is a nice conjugacy in this activity. And that's a good indication of potential Parkinson instability effect on the TID excitation. So next one I showed yesterday in my presentation. And this one is showing you really the statistics, not quite statistics, it's overall observations using our data set from 2006 all the way to 2024, the end of 2024, as a function of latitude, which is a vertical axis, and horizontal is every day over these many years. So obviously at high latitudes, those are activities associated with magnetic disturbances or auroral activities. And the lower, there's a background red curves, which is the solar cycle F10.7 indexes. So you can see that the most obvious activity occurs in December in both northern hemisphere and southern hemisphere. So there's enhanced activity December every year, very repeatable. And this is the main activity during this time, which is 9:30 in the morning. And then there's a secondary peak, which is in July and June, northern summertime. And you can see this here, June, July over here, and every year. So this is a highly solstice phenomena that occur in December and July, and it's very, very repeatable. So, and there's a solar cycle variation in terms of this, the absolute TEC fluctuation component, ATEC, and high solar activity years, you have high ATEC, and low activity, you have low TEC. And so that was morning hours, and this one is 21:30 in the evening hours, just after sunset. So most obvious feature is at equatorial region where there are bubble development, and you can see this. But at median altitudes, those are significant TID activity as well, just like in daytime. But the relative changing, the changing between daytime and night has been different. Here, if you remember, in December, there was a major activity, but here in December, it's less as active as in June and July. So the main enhancement is in July. So this is in nighttime, which is different from daytime. But obviously, so there's still a this is characterized by the solstice features. So this one shows the relative intensity of the MSTID activities. So clearly also very January and December, and the solstice phenomena with enhancement in summer and winter times. And it's very consistent between northern and southern hemispheres. So this kind of climatology is, we are trying to understand whether this climatology pattern consistent with observations from low altitudes. So we're using ARIS measurements at different local times, at different longitude sector. So this is showing the results from Eastern American longitudes. You can see significant activity and repeat every year in winter time. So this is a very, very well-known wintertime gravity wave forcing, and that is consistent with our MSTID variations. So these are observations we did next is to compare with the Welcome X simulations. And these are some examples. As I said, this simulation was run over the entire year we process the simulation data using exactly the same method we process the GPS data. So you can see clearly the fluctuation, as you see here, at different parameters. And top left is the electron density fluctuation at 350 kilometer altitudes. So those are wave fronts, and there is also solar terminator, which is parallel to the wave fronts after sunrise. And so we do the same thing as the TID. So here, example is the kilograms based on the Welcome X simulation. So you can see the wave propagation southward after sunrise in different parameters. So this one is a more concrete comparison between the GPS observation and the Welcome X simulation. So the left panels are observational, the occurrence rate as a function of day number of the year, which is the season in the vertical axis, and horizontal is the local time. So in observation, you can see clearly after sunrise, and there's enhanced activity, the occurrence, and in summertime, which is the middle part of the panel. And the top is the winter time, so you can see winter time there's enhanced activity. And the night time, you can see in observation in summertime it's pretty active. In comparison here, the bottom panel is the Welcome X simulation. And you see the winter time is highly active during the day. And after sunrise, there's higher activities. And there are differences. For example, nighttime, in our measurements, there's activities very clear. But in summer, in the simulation, it was not very evident. So this is the occurrence. And this one is the propagation direction. So most of the times, the daytime hours here is the blue, which has significant south and southeastward component. And nighttime is either north or southward, but with significant eastward component. And observation and simulation are very, very similar in terms of this propagation direction. So I'm going to skip this one. And this one, I think, is going to be a very interesting topic. Because we have 25 years observations, we want to understand whether this TID has some kind of intensification over the 25 years. And this is sort of related to the climate. We know because of the climate changing, there are significant extreme weathers that may occur more often than before. So we want to know whether TIDs or gravity wave have similar trends. So we're looking at the trends. So these are the trend results. And this result is after removing the fact that there was solar cycle dependency and there's a little magnetic disturbance dependency. After removing all of this, and you see the trend term, which is red, indicating the gravity wave intensity is getting more and more intense. So this is a positive effect. And we know, as I said, because of the climate change, many things can happen. One of the reasons maybe is the sourcing activity. The other maybe is the propagation condition. The winds condition can be in favor of the TID measurements over the high latitude regions. So the final one, the final slide, sorry. So this is very important aspect because we found that if you look at annual variation in TID activities, there's a significant QBO signature in the TID activities. So this is also indicating that what we observed in the ionosphere most likely is coming from the impact at the lower, very low altitudes because the winds will be changing due to the QBO. And I think that's it. Thank you so much.
Thank you, Shunrong. We have time for one very quick question.
Hi, my name is Prasoon, and this was a very good talk. The research work and everything was very good. I have a question that, are you updating the code for the MSTID direction for the years of solar minima? Because it's very hard to find the TC variations over there. which are like less than 5 TeC unit?
So what we did was actually to using the percentage variation. You have a good point. The solar minimum is even some of the nighttime, the fluctuation component can be very small. But if you look at the percentage changing, you can see the signature. It's very clear.
Okay.
I can talk with you later.
Okay,
Thank
thank
you
you,
so much.
Shunrong. So the next speaker is Komal Kumari from the University of Illinois. And Kumal will talk about some high-resolution WACM results. Okay.
Okay, so hello everyone. This is Komal Kumari. I just want to present some of the work that I did when I was at NCAR. So I'm going to basically talk about global characteristics of medium-scale traveling ionosphere thermosphere disturbances, or as we also know MSTID in TEC, and when we talk about MSTID like fluctuations in the neutral part, that is thermospheric winds, we call that as MSTIDs. So I'll talk about the global characteristics of these MSTID, mainly during major sudden stratospheric warming event. The analysis basically uses high resolution WACM X simulations. So we all already know a lot about sudden stratospheric warming, or SSWs. I don't want to explain a lot about what is SSW, but major SSW is basically when not only the temperature is suddenly increased in polar stratosphere, but also the polar jets starts to reverse its direction. So, and polar vortex can also split. So we also know a lot about that, how SSW modifies significantly the atmospheric dynamics, including tides and planetary waves, and as well as it can change the mean state of thermosphere. So we just heard about MSTIDs in GNSS data. So I'm not going to introduce what is MSTID here, but just that in terms of spatial characteristics, they are mesoscale structure of 200 to 1200 kilometer wavelengths, horizontal wavelength, and their period can be up to 15 minutes to 1 hour. And these are the disturbances which are really important for prediction accuracy, up to 10 to 15% in GPS TEC. They are known to be associated with sources from above, such as aurora and geomagnetic activity, and from below, like lower atmospheric gravity waves. And there are other sources such as Parkinson's instability and such. So here, basically, one of the goal here is to most observations that most study that we know of MSTIDs or MSTIDs are from ground-based observation, and they are spatially limited. So there is a lack of global observations of MSTID. So we don't really understand how the ionosphere and thermosphere couple at these mesoscale. And here I'm spatially going to talk about during the SSW event. So what is the state of knowledge? That there was this very nice paper by Nathaniel Frissell, ETL 2016. He showed using mid-latitude supertarn network observations of electron density fluctuation that MSTID activity can really decrease after the SSW onset over mid to high latitude, but with a delay of 15 to 20 days. And recently there was a paper by Sophie Phillips, ETL 2026, and she showed at high latitude, basically this decrease in MSTID activity has to do a lot with the reduced lower atmospheric gravity waves. So here, basically using high resolution WACM X study. We already heard that it's a really high, the spatial resolution is 25 kilometers, so good enough to resolve the structures of these MSTID or MSTAD. And So, but here I'm only using hourly high-resolution workup data just to, save simulation time and storage capacity and analysis time. So, but what it doesn't allow me to do, temporal filtering, but what it allows me to do at each hour, I can do spatial filtering on MSTID spatial scale. So here I'm doing a filtering of 300 to 1200 kilometer spatial scale to get the MSTID amplitude. For example, here I'm showing TEC on top, and on the bottom I'm showing how the filtered MSTID at 300 to 1200 kilometer looks like. So I forgot to mention, I'm basically using Morlet wavelet filtering. So what I do at each latitude and each UT, I am doing this filtering at these spatial scales. Okay. So here I'm just going to now show the global characteristics. So I've chosen two SSW events. One is 2012, 2013 SSW, and another is 2018, 2019 SSW. They both are well-studied SSW events, and they both were major SSW events. So on top, I'm just showing the stratospheric condition of temperature and wind, and the red dotted line basically shows where roughly when SSW onset happened. And on the bottom row, I'm showing two plots, which is basically the zonal and diurnal mean of the MSTID amplitudes in TEC. And so on y-axis, you have latitude. On x-axis, you have day-to-day, so starting before SSW onset and onwards, after, including after SSW onset as well. So what you really see that after that red dotted line, like you see this very nice enhancement of MSTID amplitude at low latitude. So that's very interesting, and that's happening in both. So because 2012-13 is solar maximum year and 2018-19 solar minimum year, so we see this enhancement in MSTID amplitude at low latitude in both solar maximum and solar minimum condition. And this enhancement is up to 1 to 2 week scale. So, I mean, I don't really have any study, to my knowledge, I don't have any study from observation verifying this. So I welcome anyone here who work with the observation to let me know if they find something like this at low latitude during SSW onset. So, okay, but I do have observation MSTID activity in the Superdarn observation done by Nathaniel Frissell. So I thought I will verify that. So his observation was mainly for the Superdarn network at mid to high latitude. So what I'm showing here on the top row is the MSTID amplitudes from high resolution Wacom model at mid latitude, so 30 to 70 north, that's the y-axis. And the KP index is just overplotted. And in the bottom row, the green line that you see, that is the MSTID activity index from Superdarn radar network. And again, the red dotted line is what shows you the SSW onset. So here I just played with the color a little bit, and what I want to show the black, the dark red or black color that you see on the top row, that's where the MSTID seems to decrease significantly. And that pretty much matches with, like in terms of when the MSTID decrease that I see in model, that matches very well with the Superdarn observation MSTID activity index. So it's one thing I wanted to point out, that in the model, I'm doing spatial filtering, but in the observation, it was mainly the temporal filtering that was done. So it's, and also the method to get the MSTID activity index in the observation was very different. So from what I'm doing from the model. So it's really interesting that at mid to high latitude, the model and observation seems to agree. So another point I wanted to, another thing I wanted to show, what about the MSTID structures in the thermospheric winds, right? So similar analysis I did for thermospheric zonal wind and the meridional wind. So on the top, again, you see the same plot that I showed before, and here I'm only showing for the 2018-19 SSW. So on the top, you see the MSTID in TEC, for the 1819 SSW event, and in the middle you see MSTAD amplitudes in the thermosphere zonal winds, and in the bottom that's in meridional winds. And basically these amplitudes are averaged for 120 to 200 kilometer height, so thermospheric heights. So what you see that the same increase that I saw in MSTID amplitude in TEC, I see the same time the MSTAD amplitude increase in thermosphere zonal wind and meridional wind. So that's very interesting. But another interesting point is that the MSTAD amplitude increase in thermospheric winds is happening in southern hemisphere. So, here we are talking about interhemispheric response to SSW on major scale in the thermosphere winds. So, global scale kind of influence. So this also points out that the thermospheric wind is in a way driving the increased MSTID amplitude in TEC at low latitude, and primarily through the field-aligned wind drift. So, okay. Now, another thing I wanted to check with, because MSTAD can have sources from above as well. So model gives you this opportunity to put the Kp and F10.7 constant, so you can really single out the forcing coming from below. So here I'm showing the bottom two plots, the middle and the last plot. It's basically from the MSTAD amplitude in thermospheric zonal and meridional winds for constant Kp and F10.7 conditions. And we see the same increase that we saw for variable geophysical conditions. So this gives us confidence that the increase in MSTAD amplitude that we see in southern hemisphere is coming from lower atmospheric forcing associated with the SSW. So this is another thing I wanted to point out, that I remember studying from Astrid Mote ETL 2016 and Petala ETL 2014 paper that semi-diurnal tides respond strongly to SSW, and they can have interhemispheric enhancement. So I thought to check the semi-diurnal tides during this 2018-19 SSW event, and basically I'm showing you here the migrating semi-diurnal tides. So on the top, just the MSTAD amplitude in thermospheric winds, and on the middle and the bottom, basically showing you the semi-diurnal tide amplitude in thermosphere region, 120 to 200 kilometer. And what is interesting, that the similar enhancement in the tidal amplitude, and that's when we see this MSTAD amplitude enhancement in the winds, and everything happening in southern hemisphere. So this made me think, what if the tides have a role here in terms of supporting the propagation of lower atmosphere gravity waves above, and further manifesting as MSTAD in winds, or there could be change in mean winds, which is playing a role for both tidal enhancement as well as MSTAD enhancement in thermospheric winds. So this is something that we have to explore further. But that's all my conclusion here. And yeah, thank you.
Thank you, Kumal. So we have time for questions.
Yeah, I might miss your talk. So you show a slide showing the TID and the TAD. So the TAD is actually the background winds, or it's actually TAD.
TAD is same scale of fluctuation in thermospheric winds, neutral winds. Yeah. Mm.
Yeah. So the TID you are using in magnetic coordinates, right? So
no, just I didn't use magnetic coordinate to explain these. Yeah. But when I will look into how the field aligned drift mechanism is working, I think I'll have to look into the magnetic coordinate. Yeah. Thank you.
One more question over there.
you were showing MSTIDs at the equatorial latitudes as well, right? So those MSTIDs at the equatorial latitudes has anything to do with plasma bubbles, or are you sure they are MSTID rather than bubble signatures?
Well, for bubble, I guess you'll have to do more analysis of the instability
those
reason. But here, I'm just doing spatial filtering on
Are those daytime or nighttime when you show?
I did the diurnal mean, so 24-hour mean of amplitude. So very simple overall analysis. Yeah.
Okay.
So I didn't do daytime versus nighttime. Yeah.
All right. Thank you.
Our next speaker is Ben Martinez from Utah State University, and Ben will show us some gravity waves from the OR mission. Ben.
Hi, everyone. Yeah, I'm Ben. I'm a recent graduate from Clemson and currently a postdoc at Utah State University. And I'm going to be talking today about the gravity wave response to a minor SSW that occurred in the southern hemisphere in northern hemisphere summer 2024. Okay. So just to outline my talk, the event occurred from July to August. From July to August 2024. The data we're using here is data from the AW mission. And for our wind background, we're using Jawara reanalysis, which is a reanalysis data set from the Gaia model that extends into the MLT. So I'll first give some background on the SSW, then a dynamical overview of the event from Jawara, and then we'll talk about the actual gravity wave variance that came out of that. Okay, so first, just a SSW. They've been mentioned already in the session, but an SSW is a dramatic meteorological event where the polar stratospheric temperatures rise tens of degrees over a few days. So far, we've talked about major SSWs in this event, and a major SSW is where the westerly winds of the stratospheric polar vortex completely reverse direction and become easterly at 60 degrees latitude. In contrast, a minor SSW has a temperature rise in the polar stratosphere, but the westerly winds decelerate, but they don't reverse all the way to eastward. And so the absence of a zero wind line can make the gravity wave response very different to a major versus minor SSW. So then just a tiny bit of background on the AW instrument. So it has 4 wide field telescopes that measure OHP1P and the Q emission lines, as well as the nearby background. So the OH reflection off the ground is less sensitive in the Q line, so we're going to use that for this study. Okay, so just how we're quantifying gravity wave activity, we're using variance. So here's an example of an AW orbit, and what we do is we take a 200-kilometer circle and calculate the variance within that circle. And that gives us a proxy for a gravity wave activity. So you can see here, if we do that, can you see my mouse? Oh, yeah, okay. You can see that these waves correspond to enhanced gravity wave, this enhanced variance, and hence that's our proxy for gravity wave activity that we're going to track. Okay, so here's the actual dynamical overview of that SSW period. So here is temperature from Jawara. And you can see temperature peaks in the stratopause in the southern hemisphere. You can see a peak in July and a peak in August. And this is our SSW, or SSWs, depending on if you want to call this one or two events. As for temperature, you can see this is wind anomaly. So it looks like a reversal, but it's actually just a deceleration. But you can see a very dramatic wind deceleration extending from roughly 30 to 90 kilometers with the second, in July. However, we're only going to talk about the August part of the event because AW was not collecting data during July, unfortunately. But here are here's the temperature from AW. You can see that AW is showing a temperature enhancement. A temperature depletion, right? Here's the enhancement followed by a depletion, orange to yellow. And then as for the variance, so the actual gravity waves, you can see if you look right here, this is our depletion and gravity wave activity. So there's an enhancement in gravity waves here on either side, but then during the actual event, there is this relative depletion in gravity wave activity. So then just to now compare it to the northern hemisphere SSW that occurred that same year in the winter. What this is this is the radiance variance prior to the SSW period, and then this is during the SSW period, and here's the difference, and the same thing for the northern hemisphere event. And just what you can see is that in general, this figure is darker blue than the one above it, which just indicates that overall there are depletions in gravity wave activity during the SSW compared to before and after. However, there are also some regional enhancements, and that's what we're going to be looking at a little bit here. So now here is a Hoff-Muller plot, longitude on the y-axis versus time on the x-axis of the gravity waves from 45 to 55 degrees south, and then zonal winds at 60 kilometers in altitude. So what you can see just by eye, there is pretty good agreement between the two of them. So the background winds have these enhancements that are co-located with enhancements of gravity wave activity, and they seem to be propagating in the same direction at the same velocity, roughly. So now, just to look at that propagation velocity a bit more closely, what we do now is we take essentially this figure, but we run it through a FFT and just extract the 20 largest amplitude waves and then plot the reconstruction of those waves, just to filter and keep the dominant wave structures that are there. And so what you can see here is that so following the SSW, these waves are propagating at almost the exact same direction in the background wind as they are in the AW. So these large-scale enhancements in gravity wave activities are moving with the wind background. So then the question is, why do we have that motion? Why is there this large-scale motion in the gravity wave anomalies? And we attribute those to the planetary waves that are ultimately driving the SSW in the first place. So here's a wavelet of the Jawara winds, or sorry, not a wavelet. This is the wavelet. Okay, so here is the wave amplitudes from wave number 1 through 5 for eastward planetary waves. And you can see during the SSW, you have a strong enhancement at 60 kilometers that peaks during the SSW. And there's still some enhanced activity before that, probably associated with that earlier event that we're not looking at. And then to see which the period of these waves that are enhanced. Now we have the wavelet, and you can see there's an enhancement in the 16-day eastward traveling planetary wave, as well as the 2-day planetary wave, both with wave number 1. And then you can actually just see that by eye. These velocities are consistent with the 16-day planetary wave that we see in both. So essentially what's happening here is that the eastward traveling planetary wave is enhanced during the SSW, and then that changes the background wind, changes the filtering conditions for gravity waves, which imparts the structure of those planetary waves on the gravity waves, and that's how we get this planetary wave signal in the MLT gravity waves. So just to conclude, we looked at this minor SSW in August 2024. And we find that the response is largely similar to the northern hemisphere SSW, where we were seeing bulk depletion and gravity wave activity. Following the onset of the SSW, there's this these large-scale eastward propagating anomalies in gravity wave activity, which we are attributing to planetary wave activity. And the dominant components of those planetary waves are the 16-day and 2-day eastward traveling planetary wave number 1. So that's all.
Thank you, Ben. We have time for questions.
Thanks. Great talk. You probably said this, but I may have missed it. So Jawara, these are meteorological reanalyses you got from the Japanese.
Yeah.
Are they free? Are they publicly available?
Yeah, these are all public on the, yeah.
And again, you may have said this, but what are they assimilating? What is the information that's going into their reanalysis products at the awe?
I believe they're simulating SABRE.
Assimilating SABRE?
Yeah.
Okay. And have you used or have you looked at other, sorry, I'm asking 3 questions instead of 1. Have you looked at other meteorological analyses like the GEOS 5 or the NRL system to provide the context for these?
We looked at MERA too as well, and we
Okay.
found pretty much consistent results where there was overlap, but we haven't looked at the other high top reanalysis.
I'm going to put you on the spot a little bit. How come you haven't been looking at the NRL?
How come we've not been looking at the NRL?
The Naval Research Lab, is part of the AW team to provide meteorological reanalyses.
True.
Okay.
I had Jawara on my laptop at the time. So,
Okay.
Yeah.
Thanks.
But we can check that as well. Yeah.
Okay, so any more questions? I don't see any. Oh.
Hey Ben, that was a great talk. At Jawara, comparison with all, there was a time there, previous slide, that one.
Mm-hmm.
At the very end there, between 21st and the 25th of August, there's a large blob in
Mm-hmm.
Jawara that is not present in the all gravity wave.
Mm-hmm.
Is there like an explanation for that?
Yeah, no, that's a good question. So I'll say first, we're still working on the mechanism right now. I think that's kind of, and like why this correlation exists at some times as opposed to other times. So I do think one thing is we're at a fixed altitude with Jawara. We're looking at 60 kilometers, which is between the two of them. And I think what could be happening is that correlation could be moving to a different altitude, and the filtering is occurring elsewhere at that time. That's my suspicion. So I expect that if we just like shift the altitude, we'll see a similar blob, or not. In this case, it would be a depletion in the winds. But we're working on that.
So all does temperatures, and Jawara does temperatures. So did you do the comparison between Jawara and all, and how did it look?
For the temperature between Jawara and all, I don't think we did, or I didn't do that yet. But we have compared, or not. Other people on the team have compared awe temperature to SABRE, and that looks good. But we haven't compared to the Jawara temperature yet. No, it's a good idea though.
Okay, so I know Titus has a comment, but I think we have to move on. Thank you, Ben. The next speaker will be Pavel Inchin from CPI, and Pavel will talk about MSTID forecasting.
The mouse. Yeah, all right. Good morning to everyone. My name is Pavel Inchin. I'd like to present some of the progress we made on the development of short-period gravity wave-driven atmospheric disturbance forecast system. And I'd like to acknowledge the contributors to this work, Steve Eckerman and Kate Zodi from NRL, and Hal Knight and Dave Brotman from CPI. So short-period gravity waves with a period down to roughly 12 minutes are known sources of atmospheric disturbances. But their forecasting was historically computationally prohibitive, and only their effects were included in the forecast through the statistical parameterization schemes. But these schemes do not lead to resolve direct phase progression of the waves and their impacts on the atmospheric plasma, not necessarily the right spectrum of generated gravity waves. So what you see on the slide, total electron content, fluctuations driven by the tornado outbreak on 28th of April 2026. And we see this massive MSTIDs over the whole United States. And this is important to highlight that these MSTIDs were observed for 5 days in a row. So these are important drivers from below in the ionosphere. Gladly, recently there was a bunch of studies that demonstrated accurate replications through the models of gravity waves and related MSTIDs comparing with the observations. But still, all these studies were targeting some historical events for the scientific purposes, and the forecasting of this small-scale gravity waves and MSTIDs in the reasonable time frame of forecast is still challenging. So to address this, we recently developed a new layer within the new NRL's ground to thermosphere and ionosphere forecast system. Specifically, we coupled Fourier gravity wave model system with NWP Neptune from NRL called Neptune, and NWP called Neptune. And with this coupling, we can rapidly resolve short-period gravity wave generation propagation from 40-kilometer altitude and roughly exabase. And the background atmospheric state and winds for these wave propagation models are used from the so-called Neptune HA forecast model. And eventually, both Neptune HA and FGMS results are used as input to NRL SAMI model to produce global, comparatively low resolution forecast, but also local high resolution regional forecast of MSTIDs. So this is a result of the validation of the system. So the top left demonstrates vertical fluid velocity slides at 250 kilometer altitude at 3 moments of time from our wave models. Oh, actually, I need to mention here that we also included MAGIC and Gemini 3D into this modeling pipeline, but currently just for model cross-validation purposes. That plot to the top left, the snapshots of gravity is at 250 kilometers. For this particular validation purposes, we run Neptune HA at comparatively high resolution, still not high enough as our wave models. So we may see that the morphology of fluctuations driven by gravity waves between wave models is fairly comparable, and the same can be said about the amplitudes. So Neptune shows the same gravity waves, but the amplitudes are smaller, and this comes from, as I mentioned earlier, the insufficient resolution in order to resolve the small-scale gravity waves, so there is plausibly excessive numerical dissipation in the simulation. So the middle panel shows SAMI 3 and Gemini 3D results that are coupled with our wave models. And again, we see, and this is total electron content snapshots. So we see, again, fairly consistent MSTIDs resolved in different configuration of our system, including different coupled models. And to the bottom right, we demonstrate observed and simulated slant TEC to recalculated to vertical TEC. So again, fairly good agreement with observations towards morphology and characteristics of MSTIDs with a difference in amplitudes of these fluctuations not exceeding 10 to 30%. And it is also important to validate the spectrum of resolved in different models, gravity waves. So the top row shows the wavelet transforms of W at 250 kilometers over just one location. And as can be seen, so all the wave models, MAGIC and NML and FWKB, show the same peak of gravity wave periods, roughly 19 minutes, and the second peak of 25 minutes. And Neptune HA resolved the same gravity waves as I mentioned earlier. But again, due to lower resolution, it does not reveal that clearly the peak of 19 minutes and only 25 minutes. But the horizontal wavelengths are fairly consistent between all the simulation and are about 210 to 120 minutes. Now, we are currently stress testing this system based on different dynamics, regions, and tropospheric dynamics, and ionospheric ambient state. So these are the results for the convective system over Midwestern United States on May 4th, 2020, as observed and simulated. These are total electron content in Magic Gemini 3D and NML Gemini 3D models. And there's a couple of more case studies for the tornado outbreak on May 3rd, 2020, and another weather system on May 5th, 2020. So fairly good agreement overall with some deviations in terms of amplitudes. So in order to push this system into the operability, we recently developed the so-called HPC master controller, which is basically just a friendly user access to run this system and sweep of forecasts with different kickoff times, different regions, or we can run many individual forecasts and then merge them together and so on. So here is just an example. This is a 4.5-day gravity wave forecast. And to achieve this, we run 26 individual forecasts, which were then just merged. And they were run in parallel on 26 nodes on DSRC Blueback HPC. And we got this forecast just in 20 minutes clock time, and the computational cost of this run is roughly 1,000 core hours. And I'd like to mention that here, these are the numbers for the gravity wave forecasts only, not including Neptune and WP and Neptune HA runs in SAMI. Now, admittedly, the core models of our wave propagation system are Fourier-based models, and they may not resolve all the gravity wave dynamics. For example, the mountain wave breaking and generation of secondary waves. And for these purposes, we, as I mentioned earlier, we use a nonlinear compressible model MAGIC. So as shown on the slide, we recently performed a case studies of mountain waves generated over Rockies, and they're breaking below the mesopause and generated a very broad range of secondary waves. And to the right is a comparison with total electron content observation. I'd like to note, so the resolution of this and WP run is E256, so it's basically a 12 kilometer or 10 kilometer resolution. And MAGIC simulation was run at, at 500 meters. So we need to be sure that we accurately resolve not only MSTIDs, but also the sources of gravity waves in the troposphere. But I need to admit that this forecast or the simulation was achieved at much higher computational cost because here we use just regular MAGIC model. And we are looking forward to the results of the ongoing ONR's Mitigate project, where IMR-based versions of MAGIC and Gemini run under the same modeling framework called Figments are used to study tropospheric weather, generated gravity waves, and their impacts on the ionosphere. So at the conclusion, the system we developed provide efficient approach for the rapid forecasting of short-period gravity waves generated by tropospheric sources and their impacts on the ionosphere. So multi-day gravity wave forecasts can be produced within 20 minutes for the region roughly 30 by 30 degrees. We could produce even global forecasts of gravity, of the small-scale gravity waves, but that would be impractical from SAMI 3 perspective. So we also found through the case studies we performed that the accuracy of gravity wave forecasts is highly sensitive to the specification of atmospheric state and winds, especially in poorly constrained thermosphere, as expected. But we found that our wave models resolve gravity waves at least with the same accuracy as what you would get in Neptune HA directly. Although in Neptune HA, it would be 10 times more computationally costlier. So thus, if we have sufficiently accurately resolved sources of gravity waves in WP and ambient state in the HA version of Neptune, FGMS can reproduce gravity wave signatures with reasonable fidelity. And finally, we found that the morphology is commonly resolved very well in all simulations, and we have differences in terms of amplitudes of simulated MSTIDs plus minus 30%. But we do not find any systematic bias here, and the difference in amplitudes appear on case-to-case basis. So we expect that these discrepancies are coming from the imperfections of the resolution of background atmosphere and ionosphere in Neptune HA and some mineral models. So we are currently performing more cases to understand the limitation of this system and approach and requirements. So that's all. Thank you very much.
Thank you, Pavel. Cool results. That's Hanli.
Thank you, Pavel. That's very interesting. The two slides ago, yeah, this one from the, it's called FGMS, right?
Yep.
The gravity wave model. It shows very coherent wave structures, while in observations, it's messier. So I wonder, in this gravity wave model, what do you use for subgrid scale? Say if the model, if the wave breaks, do you use any turbulence?
So for these purposes, we didn't use FGMS because these are Fourier linear models, right? Here, for this case study, we use MAGIC, resolved at 500 meters. So there are no any subscale schemes used in MAGIC. So it's just explicit model. We get what you get. Yeah, I don't know. So I think there is some problem. I was looking also at the same stuff a lot. I think there is some problems in resolving the winds in the Neptune HA. That was my conclusion eventually, because it was a cold air outbreak in 2022 in December, and the stratospheric winds had very complex morphology, so probably that was the cause.
Very nice talk. I concur with Hanli. A question about the comparison. You're saying that you compare the morphologies are the same in observations and your model simulation, which I interpret as that you have compared only the amplitudes, not the phase, right?
So yeah, that is a very nice point. So the philosophy of what we have is that we are not trying to resolve every MSTIDs face-to-face. That I think pretty much impossible. With the amount of data we have to assimilate these models and knowledge of the background state, atmosphere, and ionosphere, so overall we want to resolve wave fields or MSTID fields. And we want them to be as close as possible to the reality, but we do not here to resolve face-to-face. We do it though, for example, for tsunami driven by gravity waves we showed yesterday, where you can resolve even up to the phase and arrival of the signal. But here the source is much more messier. So. Yep.
Okay, thank you, Pavel. I hate to cut this discussion short, but we have to move on. So the next speaker will be Deepali Agarwal, and Deepali will talk about how the Madden-Julian oscillation couples into the ionosphere, so the physics, how that actually works. Okay, so here we go. Deepali.
Thank you. I'm just going to make sure I know. Okay. Good morning, everyone. I am Deepali Agarwal, just finishing my 4th year of PhD at Clemson University. Today, I will talk about MJO-driven ionospheric tidal variability. The focus will be mainly on the connection of the lower atmospheric weather with the ionosphere. Typically, this connection occurs through the dynamo process or through the field-aligned winds. So starting with a quick reminder about what MJO or the Madden-Julian oscillation is. These MJO are the most dominant intra-seasonal variability in the tropics. These are the large disturbances or the patterns which we see in the convection, rainfalls, and even the atmospheric circulations. And as you can see in the movie there, it is showing the rainfall pattern, which is the enhanced rainfall in the green color, and it is followed by the suppressed region of the rainfall, and it covers the whole globe in 30 to 96 days, which would be the period of MJO. And the most important characteristic of MJO is that these will always be the eastward propagating pattern. And as it can be seen in the convection, so it modifies the convection and the latent heating. So how the question arises is that how does this weather pattern are observed or modulates the upper atmosphere and the ionosphere, and it could be understood from the wave structure or the zonal structure of the latent heating. And it has been known for a while that the latent heating has these 4 peaks over the globe. And this is a key factor to generate the non-migrating tides. So these MJO forced latent heating combines with the day-night cycle or the diurnal migrating tide to generate or to modify the non-migrating tide, most importantly the DE3 tide, which is the diurnal eastward propagating tide. And if we take the diurnal spectra of this latent heating, note that these are not the same time period. This latent heat flux was plotted by me, but this diurnal spectra is taken from Dr. Lieberman's paper, and we see these peaks or the 4 peaks in the spectra as well in the troposphere, and it maps to the upper atmosphere and can be seen in the CEDAR temperature data as well, and it goes all the way into the ionosphere up to 300 to 400 kilometers. So this raises my science questions that we know that MJO modulates the latent heat. We know latent heat is the source for the origin or the modulation of the non-migrating tides. We see this same pattern of non-migrating tides through the troposphere, MLT into the ionosphere. So the question is, how does this MJO influence the upper atmosphere and the ionosphere, and which are the pathways these signatures goes from all the way from 10 kilometers to 300 kilometers. So there are 2 known pathways. I will talk about from MLT to F region, and we know from troposphere to MLT tides propagate freely, and in MLT they dissipate, and there are 2 ways they can take their signature into the F region. One is what I will name as electrodynamics, or the dynamo, or the E cross B drift. What happens is that in the MLT, we have the separation of charges because the ions propagate with the neutral winds, electrons stick with the magnetic field, and whenever there is a change in the zonal winds, we have this electric field formation. It maps into the F region, as you can see with the green arrows, and it distributes the plasma along the magnetic field line, and we see these EIA patterns, or the equatorial ionization anomaly. This is the electrodynamics pathway. It is well known from the literature. And the second is the dynamics, or the field-aligned winds. Specifically, the meridional winds transfers or pushes the plasma along the magnetic field lines. And this is a less known mechanism, at least through the observations. So all the studies we know is from the model, and I will also use the model simulations to answer the question, whether it is the dynamo or the field-aligned winds taking the MJO from MLT to F region electron density. So the difference between the electrodynamics and the dynamics is that electrodynamics is quicker. Once we have the electric field, it immediately maps into the F region, and we have this E cross B plasma distribution, whereas the meridional winds take some time, pushes the plasma along the magnetic field lines. So this is the key difference, and our goal is to determine the relative importance of these 2 mechanisms in transmitting the MJO signal into the F region through atmospheric tides. So this is a quick plot from the observational evidence. I will not spend too much time on the observational, as it was this published paper we had in 2025. Here I'm just showing how MJO signature looks in the 2 different regions. We have here the CEDAR data, temperature data at 110 kilometers, and the cosmic 2 GIST data, which provides the electron density in the ionosphere. This I have plotted at 300 kilometers. So this is showing the two regions. One is MLT and one is F region. And I have plotted here two tides, DW1 and DE3. DW1 is the most important migrating tide. And as I explained, DE3 is the another non-migrating important tide. And we see this one-to-one correlation as you match the peak to peak from SABRE to cosmic. We see this direct match of the MGO signal, which can be seen by the period itself and also the 30 to 96 days peaks we see. So we see this agreement between the two regions from observations, but however, we do not have many observations of the neutral thermospheric winds to differentiate whether it comes from electrodynamics or the dynamics. So the challenge is to separate these two mechanisms, and to do so, we need the model studies, and that's exactly what we did in our paper 2 analysis. So what I used is a TI-GCM model, and I nudged it with the ST-WECM-X. So the starting point would be to extract the MGO signal from the tides, and here, as I said, I'm using the WECM model. So what we do is we take our tides, daily amplitudes, and the phases. We use the 30 to 96 days bandpass filter, as that is the definition, and we only keep the eastward propagating tides because that's what separates the MGO from other terrestrial phenomena. So now we have the output, which we name as the filtered MGO signal, and it is a function of, again, altitude, latitude, longitude, and time. We take this filtered MGO signal and we make two data sets from WECM, where run 1 is the full tidal field we get from the WECM-X, and the second where we remove this filtered MGO. That means now we have tides, but they are not getting modulated by MGO. And we feed this WECM into TI-GCM lower boundary. So now we have two runs where we name it as MGO and no MGO. So if we take the difference of these two, we can tell how tides and which tides are influenced by the MGO and how much. So there is also this index, which I would be using the percentage MGO signal, which is the difference divided by the baseline run when there is no MGO. And note that we are keeping the conditions of the geomagnetic and solar flux constant and low, because I am more interested in the lower atmospheric impact. But the results would not change much because we are taking the differences. But however, the mean state could be influenced by the high solar flux. And we are only changing the tidal fields. We are keeping the mean states same. So whatever the differences we see in the upper atmosphere would come through the forcing of the MGO into the tides. So along with these two runs, we also did other runs because I was interested to see the influence of MGO in particularly DE3, or except DE3 in any other tide if other than DE3, any other tide who is influenced by the MGO, because it is less known. There are many studies on DE3 about the MGO, and there are also two additional runs if the time permits. I will talk about the influence in the migrating tides, DW1 and SW2. So these are the main key results, and I want to spend a little bit time on the slides here. Here I'm showing the DE3 tides in 3 parameters. One is the electron density, 300 kilometer, the first row. The second is the zonal wind, and the third is the drift. So what I'm trying to see here is that, can I see the similar signature, what I see in the observations, through the dynamo part? So I'm comparing these three. The first column is the output from run 1. That is when I have all the tidal fields carrying the MGO. The second column is when I'm subtracting the two runs. That means this is my MGO signal, which DE3 is carrying from all the way to zonal winds to drift into the electron density. And the third column is the percentage. It will give us the quantification of how much MGO is modulating the parameters. And again, we see we have zonal winds, which are changing at equator. It generates the electric field and hence the dynamo, which will change the vertical drifts, and these vertical drifts would give rise to the equatorial ionization anomaly. And from these results, we say that we saw this 20% modulation in the E region winds, in the F region vertical drifts, and electron density. That means dynamo is important, and we saw that from observation and the model itself. But how much it is important is the quantification. So what I did, I just chose like a slice from the last slide I was showing. This is plotted at the northern EIA. The upper plot is showing, again, the drifts, winds, and electron density, and we see this one-to-one correlation, and the correlations between these are plotted below. The first one is between the winds and electron density, the second is between drifts and electron density, and third between drifts and winds. And we see close to perfect correlation between winds and drift, which we know that dynamo, once we have the change in winds, it would quickly map into the drifts. But the correlation between the winds and the density and the drift and the density is slightly lesser than the winds and the drift, which tells us that dynamo does not tell the complete story. There is some other key parameter which is missing from it, and I want to quantify that, how much that parameter would be. So for this, I used the ion continuity equation. So that was the reason to use the TIGCM, because TIGCM has this as a direct output. We have ion continuity equation, which matches well with the electron density, so it acts as a proxy. What it does, it divides the parameters into different components. I have transport of plasma through electrodynamics and through winds, and it gives me a proxy of electron density. And you see how good of a match this is. On the left-hand side, we have the MGO in electron density, and on the right-hand side, I have the match in the change in O plus density in the ionosphere. So I take the left-hand side as a proxy of my electron density, and I divide the right-hand side into transport by drifts and transport by winds. So this is a busy slide, I know, but I just want to show here that we have 3 different runs here, or the 3 different differences. The first one is when all the tides have MJO. The second column is when there is no DE3 taking MJO, and the third is when there is only DE3 taking MJO. And the line plots are nothing but like a slice plotted here. So the red one will show when there is no DE3 carrying MJO, and the red one is when DE3 is the only one carrying the MJO, and the blue is when there is no influence of DE3. And if we divide these two transport by drifts in DE3 versus non-DE3, we get 73% enhancement by electrodynamics and 65% enhancement in other tides by winds. So what we say here as DE3 is the dominated by the electrodynamics effect, but the other tides, which we do not know as of now, are influenced by the wind dynamics. So to understand that, we see this structure, this enhancement when there is a weather change, when there is no influence of DE3, so what could it be? So we know the other important phenomena is the wind dynamics, and that's exactly what we looked into. We saw the wave 4 structures because wave 4 is the one influenced by the latent heat, and we looked into the meridional tides because that's the one controlling the wind dynamics. And we saw that SE2 is the other tide, and it has the same structure of MJO, which we saw in the previous slide, which would be another important tide carrying this. And this is the comparison of DE3 and SE2, which tells that DE3 is almost double as SE2. So my conclusions, I will skip the mean state, but we also saw the influence of MJ on the mean state. So the conclusion is that we quantified that there will be 20% variability in all the parameters. DE3 is the most important tide carrying the weather signature into the ionosphere, and the mechanism controlling it is electrodynamics. The other important tide is SE2, so it cannot be also ignored, but it is almost half of the influence of DE3, and it is mostly controlled by the winds. So that would be it. So these are my 2 papers, and I'm also looking for postdocs, so if anyone has any openings available, let me know. Thank you.
Thank you, Dipali. So we have time for one very quick question.
It's a really great presentation. Thank you. I learned a lot. I was wondering if you could speculate on the connection between your work and maybe the impacts on spacecraft operators.
Yes, that's the slide which I missed. I mean, for the spacecraft operators, we are more interested in how the neutral mean state would change the path of the orbits, and that's what we saw with MJO. I saw the total impact to 5%, so it's not as big as the geomagnetic storms or even SSWs, but it is something which cannot be ignored. And the most primarily tides which would be controlling is the semidiurnal tides. So we should implement these tides and the MJO into the models while calculating the orbital precisions and all.
Okay, thank you, Dipali. We have to move on. The next talk will be given by Latoya Wilcoxon from Arizona State University. And she will talk about what very strong thunderstorms do to the ionosphere and thermosphere, right? Okay. Okay.
Awesome. Thank you so much. Hi, everyone. My name is Latoya Wilcoxon. I work with Dr. Katrina Bowser at ASU. Today we'll be discussing the influences of Draco storms on the ionosphere and thermosphere, gravity wave coupling, and thermospheric wind interactions. So for this research, we're looking at gravity wave generated from tropospheric sources, such as when you have a convective thunderstorm in the troposphere that creates an overshooting cloud top plume that punctures the tropopause, that creates concentric gravity wave ripples that are able to vertically propagate into the upper thermosphere. And gravity waves prefer to propagate in the opposite direction of the background winds because they're moving slow enough if they encounter a wind reversal and they're moving in the direction with the background winds. This can cause gravity wave saturation and forces the gravity wave to dissipate and break, which further injects the momentum and energy upon breaking. Another way for these gravity waves to vertically dissipate is through viscous dissipation, which occurs when the propagating gravity wave's motion is dampened with altitude due to internal friction. Once again, once these gravity waves break, the momentum deposition is injected into the background atmosphere, which causes an acceleration on the background winds. And this is supported with the Vadas et al. 2014 paper, which shows perturbations of hundreds of meters of wind acceleration due to convective gravity wave breaking. So the research presented right now focuses on observational studies of sustained gravity wave thermospheric impacts on or from deep overshooting cloud tops associated from Draco-type mesoscale convective systems using the June 29th, 2023 convective events as a case study. This observational analysis investigates an overlooked type of mesoscale convective system and its impacts on the thermosphere through deep convective sources. So defined by the National Weather Service, a Draco is a severe thunderstorm that has wind damage swaths that extend more than 200 miles and has wind gusts of at least 58 miles per hour. These Dracos can last from several to 24 hours and can span hundreds to thousands of kilometers in a day. So these storms are a source of continuous deep convection. And from this deep convection, we get overshooting cloud top plumes, as mentioned before, that can be a generating mechanisms for concentric gravity waves. And I observed these concentric overshooting cloud top plumes with GOES 18 brightness temperatures used with IGRA, which is your integrated triple pause temperatures. Once you get your triple pause temperatures, you're able to see the overshooting cloud top plumes that puncture this region. And then here we have the map that illustrates the evolution of overshooting cloud top plumes throughout the storm events that could create these concentric gravity wave rings. So here we have our GNSS observations, if this could play, the gravity and acoustic wave generation throughout the day or throughout the convective events on June 29th. We see our acoustic waves in the 10-minute high pass, which responds very quickly to these overshooting plume stimulus. At the moment, this storm is in its early phases. The mesoscale convective system has not further matured, so we're seeing early convection from pretty weak convective overshooting cloud top plumes. But as this storm continues to mature and the Draco becomes a Boeco in its maturity, we'll start to see more concentric ring-like patterns in the ionosphere. So just to speed this up for the sake of time, as the gravity waves, or as the storm propagates eastward across the central United States, you're going to see the acoustic waves basically move with the convection in the troposphere. You're basically observing these acoustic waves that are propagating in less than 10 minutes directly over the storm. And then at the 5 to 40 minute high pass, we start to see these eastward concentric-like gravity wave perturbations coming from the maturity of the Draco Boeco within the troposphere. And so as we see these, as the storm matures, we start to see our strongest concentric ring perturbations from 17 to 19 UT, where you're seeing almost the full concentric ring pattern of the gravity wave propagating from the Boeco and the troposphere. So our acoustic waves were observed for the entire 24-hour period of this convective event, and our gravity waves in the ionosphere were observed from 11 to 19 UT, with our strongest concentric ring, our strongest observable concentric rings being from 17 to 19 UT. So we look at this storm in basically two parts. We have our first observable gravity waves observed in airs at 724.30 UT. We have our, as you see from 39 kilometers, we see our eastward gravity wave perturbations, but we're not observing these gravity wave ripples to the west because this is most likely being absorbed and dissipated into the background winds. The plumes plotted represent the plumes from 01 to 05 UT, which correlates to around the time that this gravity wave would have propagated to 39 kilometers. With these eastward gravity waves, you would expect the zonal winds to be westward as they propagate, or the favorable propagation is in the opposite direction of the background winds, which is shown with the Mirror 2 analysis of the background winds, showing westward deepening winds from the tropopause to approximately 60 kilometers. To further characterize this gravity wave, we took 3 cross-sectional periods from the same wave to get an average vertical wavelength of approximately 19 kilometers. And using the dispersion relation and vertical group velocities, we're able to characterize and calculate the total propagation time for this gravity wave to travel from the tropopause to 60 kilometers to be approximately 3 hours, 27 minutes. And at this point, we see a zonal wind reversal around 60 to 94 kilometers of deepening eastward zonal winds. So now the gravity wave is moving in the direction of the background winds, which is further weakening this gravity wave, which breaks by 94 kilometers, and this gravity wave is further inhibited in vertical propagation due to the saturation theory of dissipation. Next, we go into our GNSS tech that detected the fast, high-frequency, fast-propagating gravity waves that were able to overcome the MLT wind reversals and propagate into the ionosphere. These gravity waves are observed in the ionosphere that are being generated from the Draco-Boeco activity in the troposphere. And this persistence of ionospheric perturbations are correlated to the intensity of the tropospheric mesoscale convective system convection. To calculate our phase P, we basically took the horizontal displacement of the gravity wave perturbations from a 10-minute period and calculated a total phase speed of 178.8 meters per second, which is very fast. With this type of phase speed, it was able to overcome the MLT when it's just able to just propagate through the areas, not even really being inhibited, just because of how fast this gravity wave is moving. And it was able, or the total propagation time from the tropopause to approximately 150 kilometers, it took this gravity wave approximately 35 minutes to travel. To calculate the sustained Draco-generated gravity waves, acceleration on the thermospheric background winds from gravity wave breaking momentum deposition, using our GNSS tech data, we first needed to make a few assumptions. We don't know exactly what is happening in the upper thermosphere, but we do know that we do have significant averaging throughout the tech layer. But first, we make the assumptions that the electron density is approximately relative to the neutral density perturbations in order to calculate the momentum flux of the wave. But in order to do that, we have to add on the correction factor to account for the averaging to get a range of the momentum deposition values. It's also assumed that based on the gravity wave parameters shown in Table 3 and correlated to the Shearer-Bodas 2007 paper Figure 4, it's assumed that these ionospheric gravity waves are likely dissipating near 200 to 225 kilometers over a 25-kilometer altitude range. The calculations of this acceleration on the background winds can be complicated because the full width half max F layer is larger than our vertical wavelength, but due to averaging throughout the GNSS tech layer, the vertical wavelength and amplitude are most likely being reduced. This means that the dissipating waves at this region may be larger than what's actually being shown in our GNSS tech perturbations. So once again, to account for the vertical averaging effects, an estimation factor of 2 and 10 are utilized to estimate the potential true wave amplitude. Our gravity wave polarization relations were used to estimate the atmospheric density perturbations, where our momentum flux was used to characterize our gravity wave, which resulted in the acceleration of the background, and use our acceleration to calculate the acceleration on the background winds from the momentum flux deposition. These correction factors of 2 and 10 were chosen to span the thermosphere and ionosphere gravity wave amplitudes reported in the Sharon-Bottas 2025 paper. We have our lower and upper bound correction factors and our uncorrected GNSS tech acceleration effects. As mentioned previously, it is very difficult to calculate the exact dissipative conditions of these gravity waves at these altitudes, but we expect our observed GNSS tech gravity waves to fall somewhere in between the factored measurements of the factor in 2 and 10. And so overall, the conclusions from this research show that the weak morning convective generated propagated or gravity wave propagation took approximately 3 hours and 27 minutes to reach 60 kilometers from the triple pulse, but due to the saturation theory, dissipative processes, the gravity wave was forced to dissipate before 94 kilometers. Our high-frequency gravity waves were able to overcome that MLT zonal wind reversal in approximately 35 minutes at 1830 UT. These gravity waves are coming from a stronger source of convection from the Draco-Boweco. And then the tropospheric convective sources play a crucial role in the propagation of the gravity waves in the upper atmosphere. So our weaker convective thunderstorms created weaker gravity waves. Our stronger convective plumes created stronger gravity waves. Our sustained, and the overall takeaway from this is that the sustained thermospheric gravity wave propagation observed from 11 to 19 UT likely had a significant impact on the acceleration of the thermospheric background winds through momentum deposition. Thank you.
Thank you, Latoya. We have time for questions. Pavel?
A very nice presentation. I just wonder, so your conclusion is that the stronger derivatives drive stronger TIDs in the ionosphere, but how you discern the source effect from the propagation effect? By propagation effect, I mean the effects like wind filtering of gravity waves and other effects like braking and so on.
I really didn't hear your question too much.
Yeah, I'm sorry. Yeah, so your conclusion was that stronger derivatives drive stronger MSTIDs. How you discern the source effect from the propagation effect?
Oh, I see.
Yeah, did you do analysis of like winds during these events over the derivatives?
You said weak convective events throughout the derivatives?
Yeah, winds.
Weeds.
The winds.
Oh, winds. That's something that I could look into. As far as the background winds, I mainly see the effects of the inhibition with the airs, but for the GNSS tech, I don't have an answer to that question right now, but I do have a poster and I could go into further definition of that. I don't know.
No worries. So you can always discuss that
Yeah.
with Pavel after the session.
Yeah.
It's, okay, thank you.
Thank you.
Our next speaker is John Merriweather from NJIT, and John will talk about FBI results from El Leoncito.
Thank you. It's a pleasure to be here to give this presentation. To begin, I would like to acknowledge my contribution made by my co-author. Carlos Martinez did a paper on the climatology of winds and temperatures at El Leoncito, which is a site located in central Argentina. And Luis Navarro led a paper describing the result that we got for the May 11th storm, 2024. And also a co-author on this paper is Dr. Shenrong Zhang of MIT, who looked after the analysis of the GNSS observation from the network located in South America. The location of El Leoncito is about 125 kilometers to the east of the Andes Mountain and about 32 degrees south latitude. And to the right here, I'm showing the description of the Fabi-Perot interferometer that we used for these measurements. Fortunate to use an ultra-narrow transmission filter with a really sharp profile and a peak transmission of 92%. So this eliminates the concern about the OH contamination of the SIT-30 airglow observation. What you see in the yellow panel there is the one-dimensional spectrum associated with the interferogram, and the quality of these different orders indicate the focus is sharp and well-defined. So we expect good quality data out of these measurements. This panel shows the oscillation, vertical wind. We showed an experimental strategy in which we emphasize the cadence in the vertical direction with an occasional look to the horizontal direction, whether zonal or meridianal. So we see oscillation there with a periodicity of about 0.6 hours, and the amplitude is of the order of 30 meters per second. This set of measurements were made in October, late October. This panel showed the two additional nights in late October, the 19th and the 20th. The first night was the 18th. And all three nights showed the oscillation that you see on the first night. Again, about 0.6 hours periodicity and an amplitude of about 30 meters per second, which is quite unusual for the vertical direction. The reason for wanting to enhance the cadence in the vertical direction was we felt that that would be possibly a way of detecting the effect of gravity wave activity. This shows the zonal observation, meridianal, and the horizontal wind measurement. And what we see is a flow to the north, equatorward, during much of the night, and a flow to the east, zonal, also for much of the night. So the neutral wind vector is oriented at around 45 degrees to the northeast, which means the optimal direction for propagation of TIDs would be about 225 degrees. In other words, opposite the direction of the neutral wind vector. To assuage the concern that what we're observing is an artifact, I'm showing you the progression of laser calibration for the images that we collected during the night. We used this as a way of determining the Doppler zero for the measurement, and there's no indication of the fluctuation that I showed you for the vertical direction of the winds. So I think my concern about the possible artifact is alleviated by looking at this graphic. The period featuring the vertical wind oscillation occurred at a time when the thermal drift of the instrument reference is no more than a few meters per second. This shows the result from Shanguan analysis. Let's see. And what we see here is the wave train moving to the southwest, and the white arrow points to the crest of the wave system in the plasma distribution. So the TID shown here is moving pretty much in the direction opposite the neutral wind vector. And this shows the comparison of the fluctuation in the zenith with the differential TEC fluctuation. And there's also, on the third panel, the temperature fluctuation, and then the bottom panel, the sky intensity fluctuation. And you see that the phase relationship between the vertical wind and the DTEC is not perfect, but both set of data do show significant fluctuation. To look at the question of seasonal variation, I'm showing you the result for summer, local summer on the far left, equinox in the middle, and the winter on the far right. And you see that the fluctuation amplitude is diminished by roughly a factor of 2 for the local summer observation, which was in May, as compared with the winter observation. I'm sorry, the local summer was December, and the local winter is in the May period. So this suggests that the mechanism producing these oscillations is weakened during the local summer period. This illustrates the production of periodograms for both the TEC and the DTEC and the vertical wind. And the dominant periodicity for the vertical wind is about 0.6 hours. Dominant periodicity for the DTEC fluctuation in the zenith is about 0.5 for one night, and no dominant indication for the other night. What is producing these oscillations? This is a graphic that I found in the literature suggesting prevailing winds, trade winds, moving from east to west, north of the Air's Leoncito Observatory, which is located there. And so there's the boundary of flow direction of the surface wind. North of the boundary, the prevailing winds would tend to be from east to west. South of the boundary, the prevailing winds would tend to be from west to east, as it is here in the continental U.S. So there's quite a bit of horizontal shear between the north and south direction relative to the location of El Leoncito. So this is suggestive that there might be quite a bit of forcing of gravity wave activities that we could observe in the thermosphere region with the Fabry-Perot measurement of vertical wind. This is a graphic taken from the paper by Lund and Dave Fritz, who did the analysis, numerical analysis of the propagation of orographic wave from the surface up into the thermosphere region. The height that they published for their data was 180 kilometers, which is shown here. And you can see concentric behavior around one of the mountain peaks in the Andes. Their analysis applied to a region that's about 2,000 kilometers to the south of the El Leoncito. So this result here doesn't directly apply to the El Leoncito location, but it's certainly suggestive that orographic wave might well indeed produce thermospheric wind variation. This is an analysis of green line images taken by the Boston University imager located at El Leoncito. The raw green line images do not show any indication of wave structure, but when we do a differential analysis against the background average, we see this structure showing for 3 successive period half-hour apart. And so this suggests that there's definitely some structure going on at the height of the green line layer, which is around 100 kilometers. The analysis by Lund and Fritz suggest primary wave system going up, breaking, producing secondary wave systems which pass through the 100-kilometer region to get to higher height. The analysis of the 08 data showed similar indication of structure as to what you see here. So conclusion, summary, it looked very much as if the vertical wind oscillation that's detected by the Fabi probe might very well be a result of the breakdown of orographic waves generated by surface wind passing over the South American continent. And I think the location of El Leoncito, close to the boundary between the trade wind and the prevailing wind of the mid-latitude, is a very fortunate circumstance that will produce the phenomenon that we're showing here. It would be interesting to see whether similar results are obtained for a Fabi Pro located near the Rockies, and my colleague Jonathan Mackler will be looking into that shortly. Thank you very much.
Thank you, John. We have time for a couple of questions.
So, John, in the red line images or in anything, do you see any horizontal phase speed of these things producing the vertical oscillations?
I'm not sure I understand the question.
Do you see any horizontal velocity associated with whatever structures you think are producing the vertical velocities?
The best way to answer that question is to divide an experiment, say, looking at 3 different directions and looking for patches of irregularity, very oscillation through each one of the 3 locations and see what the phase difference in speed might be. These results do not lend themselves to any interpretation of phase speed. The TID's phase speed, which I didn't mention, was 165 meters per second, which is typical of most MS-TIDs.
But mountain waves, if they're orographic waves, they're going to have a 0 phase velocity, right?
Nominal mountain wave would have 0 phase speed, I agree, but this is perhaps not the nominal orographic wave structure. Steve Smith reported on orographic waves associated with El Leoncito, but that was very obvious a structure. What we're showing here look to be quite different. So I think more to be done to answer your question. But let me do say that we have looked off the genus in different directions, and we see oscillation in those directions.
Okay, thank you, John. So our last speaker is Shantanab Deshapuri, and Shantanab volunteered to give a short presentation. And Shantanab will talk about results obtained during a campaign with the Milston Hill ISR on convectively generated gravity waves and their impact on the ionosphere.
And here you go. Thanks, Ian. I have the misfortune of standing between you and lunch, so I'll try to not live up to that. But a lot of credit goes to Larissa and the MIT Haystack team, because it's not really easy to schedule some campaign, but we try to put something together to understand how the acoustic gravity waves are impacting the vertical ionosphere. And so I'll just speed run through this. So the idea was, to just test, like we have had many talks discussing about the effect of gravity waves on mean flow and acceleration and how that helps in or redistributes the plasma. The idea was to see if Millstone Hill can catch this particular changes. So this particular campaign, we focused on September 2 to 5, 2025. We had Millstone Hill looking vertically upwards and also to the southwest, and I mean, we had like pretty good resolution, enough to catch the waves. And to give an idea about geospace conditions and everything, it turns out, unfortunately, we were in the middle of recovery phase of a big geomagnetic storm, and the event that actually we are interested in, or the day we found some acoustic gravity waves that were convectively generated, happened to be on September 4, and this was also when we had some minor substorm actually showing up towards the later phases. I'm not showing those TIDs, but if I played this video long enough, you would see kind of those large-scale TIDs coming in that as you would typically see. And so just to give a brief outline about what we observed, I mean, there's no real quiet day in nature, right? Like, so it's, I mean, it's really difficult to get a quiet baseline established. But what we did is we tried to look at number of runs or number of zenith scans that were done the week before, and so tried to get some sort of a quiet average going. And then also to the right-hand side, you see the zenith and the MISA scans for the particular day where we observed the acoustic gravity waves, and you can see differences even in the zenith and the MISA. And a lot of differences between, say, the quiet day mean and the event day, which are the bottom two panels. So going to the event, so the left plots are the same, like, you know, the MISA and the zenith scans, and the right you see the TEC map with the next-red radar. If you can squint and see the green outlines at the back, there was a convective event, and I mean, if we zoom in into the section and do a time distance diagram, you'll see that like the waves are actually pretty large horizontal wavelengths, close to 380, 390 kilometers, time periods of about 25 minutes. And let's see what Millstone and Millstone Hill also actually, I mean, if we do a difference plots and we look at the altitude profile, we see like, I mean, similar periods also in the same time region of interest, right? Like between 19 to 16 to 20 UT approximately. So that they are the same periods that we see in TEC and also in Millstone Hill. And then the next step was to do the Magic Gemini runs and see like how much of this actually is captured by models. And so we did the you know, the conventional outline that we have traditionally used, the Steven Alexander specification of realistic sources from NextRad, and then we did the model run, and right off the bat we noticed that the amplitudes were much higher, the much higher acoustic gravity wave driven TIDs than we observed in observations, even though the vertical structure of the ionosphere is pretty much similar, as you can see on that bottom right plot. When then the next step was to see, like, you know, the whole idea about this was how much of this impacts the background. I mean, how can we quantify that? Can we, you know, understand that to the extent that we can go and say that definitively this is the impact. But when we did so Inchin et al. 2025 had some, you know, processing steps about, like, you know, how he went about and did that, and we replicated that with the same experiment. We did like a 1 hour low pass filter and tried to separate out the, you know, the background from the waves, and it turned out that the background that we saw in the observations were actually much more elevated than what the model predicted. And this is particularly because, I mean, we were in the middle of a storm. But I mean, there are some things we could do with the models as well. We use HWM. I mean, we can use more realistic winds. We can try to go for a more realistic source specification, which is, I mean, kind of things that we are even considering in a different project. But overall, I mean, the next steps is that we are doing a follow-up campaign. We are trying to go for a day where hopefully we get lucky and don't have a geomagnetic storm. It's difficult to predict these things, but I mean, we can do as much as we can. Also, I mean, I'm excited about this because, I mean, it gives us the opportunity to kind of decouple sources from above and below. I mean, if you can do the best job as we can do, possibly with modeling, maybe we can kind of establish what is impact from above versus what is impact from below, and how much of the gravity wave spectrum is contributing to the background changes in the ionosphere. So that's the you know, short summary of it, and I'm happy to take questions.
Thank you, Shantanap. We have time for a couple of questions.
A very interesting talk, Shantana. I just want to say whether you can elaborate a little bit more about what this follow-on campaign is going to be about, and a little bit more details to share with us.
Yeah, so basically we are, discussing with, basically the similar type of campaign around a week, 3-4 days. I mean, we did like 4 days last time, so probably the same later this summer. Trying to go for a period where we are, more fortunate. So basically, we did it in September, and September is not, it's kind of a bit late for the convectively generated acoustic gravity waves to really, so we are trying to go for a bit earlier period if we can. We have not really ironed out the details, so I cannot give you anything more than that, but we'll probably be in discussions and trying to, if you're interested or anything, like just, we can discuss. It's kind of within the same ecosystem of projects we're interested in. Yeah, Larissa can speak to that probably much more than me.
Just a very brief comment. We try to catch thunderstorm conditions based on predictions, and of course it's just not that easy to predict. And we were fortunate enough that we ran previous campaign in the previous week, so that really helped as a background. Because as Shantanab said, if you have 4-day campaign and you have serious geomagnetic activity on the first day and recovery after that, that really makes analysis complicated. As far as upcoming things, we have some anticipating some wall-day campaigns in August, some other things. So we will be looking for conditions and planning. And I am really excited about this work, but please be patient. Remember how we first started planning strat-warming campaigns back in 2006. We ran first campaign with wall-day campaign organized all ISRs in 2007. We caught first successful campaign was in 2008, and absolutely phenomenal things we started observing and reported. First papers were in 2009. Please be patient, we'll get there.
Okay, thank you. So this concludes the first part of our workshop. We will reconvene at 1:30 with 9 more very interesting talks, I promise. And let's thank all the speakers, and also I think we had a very good discussion. So enjoy your lunch.